Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, in section 3.2, we discussed the scheduling of batch processes. Now, in particular, we discussed the scheduling algorithms such as FIFO, the first in, first out, and also the SJF, the shortest job first, and shortest remaining time first, the SRT. Now, today, we're going to talk about the scheduling of interactive processes. Now, the interactive processes communicate frequently with the user in the form of a dialogue by receiving commands or data from the input-output devices like a keyboard or a pointing devices, and responding by generated output. So, for example, on the user's terminal or the other output devices. So that's interactive process. It will communicate frequently with users. So interactive processes are bursty in natural. So it's unlike the batch processes. So they're basically long learning processes. Once they are created, they're gonna, they're gonna be running on the CPU for a long time, and then when they quit, they generate output. But interactive processes are different. Okay, so interactive processes must time share the CPU using some kind of preemptive scheduling to give each process a chance to make progress in a timely manners. Okay, one of the well-known scheduling algorithm for interactive processes is called round-robin (RR) scheduling algorithm. So in round-robin, a time quantum. So we use Q to represent time quantum is used. A time quantum is a small amount of time. It's so small that typically it ranges from 10 to 100 milliseconds. So that means for 1 second, you probably gonna be divided. The 1 second probably gonna be divided into hundreds or thousands of time quantums. Now, during which the process is allowed to use the CPU. Okay, so the round-robin algorithm uses a single queue of processes. So if you have multiple processes running, and the round-robin use a single queue for all the processes. Now, the priority is determined solely by the process's position within the queue. So basically, round-robin going to treat all the processes the same. So they should have the same priority, except, because they're in the queue, so the process that at the head of the queue has the highest priority. So when the CPU is available, when it's time for the CPU to pick the next process, the process at the head of the queue will be selected. And then once it's done, this process will be placed back to the tail of the queue, and then pick the next process at the head of the queue. Okay, so that's how the round-robin works. Now, the process at the head of the queue has the highest priority and is allowed to run for queue time units. Remember the queue, it's the time quantum. Okay, it's time quantum. So if the time quantum is 100 milliseconds, so each process is gonna be able to run for 1 million seconds, and a switch to next process, and the next process is gonna run for 100 million seconds. Okay, so when queue ends, the process is moved to the tail of the queue, and the next process now at the head of the queue is allowed to run for queue time units. So the round robin is pretty simple in terms of the scheduling, but it will switch the process at a very fast speed, and typically you're going to switch back and forth many times in a second. Okay, now let's take a look at the example. So let's see, we have 3 processes. Okay, now the total CPU time for process 1 is 4, and total CPU time for process 2 is 4, and then process 3 is 2. Okay, and then we need to determine what's the time quantum. So now let's say time quantum is 1. So what this means that the process 1 gonna take 4 time quantums. Okay. Process 2 gonna take 4 time quantums. Okay. Now let's draw the diagram. So we have a P1, P2, P3. Now, so first the CPU may pick P1 to execute. Now let's say each of these is just a 1 time quantum, right? 1 time quantum, and this is a 1 time quantum. So these, so P1 and the P2 and the P3 are going to be in the same queue. Let's say P1, P2, P3. Okay, in the same queue. So that's the header, and that's a tail. So then P1 is selected. So you're going to run for 1 time quantum, and then it was switched out. So P1 going to be put in the back of the tail, back of the queue. So then P2 going to be and that's the header, tail. So then P2 going to be picked up. So the round robin algorithm is going to pick P2, and then once P2 done its job, then P2 will be put in at the tail of the queue, and the P3 going to be selected next. And then we go back to P1, and then we go, to P2, P3. Now remember, P3 is 2. The total CPU time for P3 is 2, which is also the 2 time quantum, right? So then we go back to P1, P2. Now since P3 has completed, so now the switch can be back and forth between P1 and the P2, and then P2, and that's it, right? So we're done. So that's the round robin. So since as I said, the round robin is basically switches back and forth at a very fast speed, because the time quantum is typically a very small time period. So it will switch back and very quickly. So this is going to cause some kind of illusion that P1 is running concurrently with P2. Okay, so now we summarize these examples with the following diagram. Okay, now let's check the performance for the round robin scheduling algorithm. So let's take a look at the waiting list for each process, and also the turnaround time for each process, and the average turnaround time, and also the waiting list for each process, and the average waiting list. Okay, let's take a look at turnaround time. Okay, so the turnaround time for P1, P1 has actually 4 sections, right? So the turnaround time for the first section is 0 to 1. And turnaround for the second section is from 1 to 4, so it's 3. Now turnaround for the fourth section is 4 to 7, so that's total of 3. And again, the turnaround time for the last part is from 7 to 9, which is 2. So it's 1 plus 3 plus 3 plus 2. So that's the total of 9. Okay. Actually, there's an easy way. You can directly count the arrival time and the departure time, right? So that's arrival time. That's a departure time. So 9, they're going to be 9 minus 0, because once it's arrival, it's complete the job at the 9. So the turnaround time for P1 is 9. Same thing for P2. You can calculate each individual part for the turnaround time, but you can actually count as a total. So it basically it arrives for P2. It arrives at also time 0. We assume that in the queue they already in the queue when we start to use the round robin. So we assume that all the arrival time going to be 0. So then we can find out that for P2 the complete time is 10 minus 0. And then the complete time is 6 for P3. 6 minus 0. Okay, so that's the turnaround time for each. So the average turnaround time is 9 plus 10 plus 6. Okay, divided by 3. So what's the value? So that's 25 divided by 3. So it's 833. Okay, that's the turnaround time for each process, and that's the average turnaround time. Now let's take a look at the waiting time. Now the waiting time for P1, again, we check each individual part. So the waiting time for the first part, once it's, it starts at time 0 and immediately get the CPU. So the waiting time for the first piece is 1 or 0. Now for the second piece, it just kicked out at the time 1, but it regained the CPU at the time 3. So the waiting time for this second block, for the second piece, it is 2, right? It's a 3 minus 1. So it's actually 3 minus 1. It's 2. And then this piece, get the CPU at the 6, and it was kicked out of the CPU at the 4. So it's actually 6 minus 4. Plus the last piece, get the CPU at the 8, and kicked out of the CPU at the 7. So it's 8 minus 7. So the waiting time, the total waiting time for P1 is 0 plus 2 plus 2 plus 1, so it's 5. Now waiting time for P2, so let's see. P2 actually first piece waited for one actually time unit. It just get the CPU at the time 1, but it's already in the queue at the time 0. So the waiting time, the first piece is 1. The second piece from 2 to 4, get the CPU at the time 4, but kick it out of the CPU at the time 2. So it's a 4 minus 2. And for this piece, it's a 7 minus 5, right? And for the last piece, it's a 10 minus 8. Oh no, I'm sorry, it's a 9 minus 8. So a 9 minus 8, 9. So that's 1 plus 2 plus 2 plus 1. So that's 6. And for P3, the first piece waited for 2 time unit. So it's actually 2 minus 0. The second one waited for, it's a 5 minus 3. Okay, there's only 2 parts. So you got a 4. So the average waiting time going to be 5 plus 6 plus 4 divided by 3, so it's 5. Okay, so that's the performance if we use the turnaround time and then we use the waiting time. So you got the, this different value. Okay. Okay, so let's discuss more on the round-robin scheduling. Okay, look at this example. It's the same example we used in the previous slide. So in that case, we have 3 processes, process 1, 2, and 3, and the time quantum is 1. Okay, so process 3, 1, 2, 3 are in the round-robin queue, and the process 1 is selected. You're going to run for 1 time quantum, and then switch to process 2, right? And then switch to process 3. And then come back to P1, P2, and then 3. Now, the total CPU time for P3 is 2, so after 2 time quantum, P3 is done. And then we switch back to P1, then P2, and P3 is already terminated, right? So we switch back and forth. Now, the good thing about the time quantum is that the round robin is it does not discriminate against any process. Can you see that? Now, let's say if you have 3 processes and the process 3 is definitely the smallest process, right? It only takes 2 time units. That's the total CPU time is only 2. And P1 and P2 are much bigger. It's double the size. It's only they have 4 total CPU time. Now, under the round robin, P3 actually finished earlier than P1, right? Even though P1 was loaded into the CPU before P2 and before P3, but P3 still finished earlier. Okay, so that means in round robin, small process, the process with a small CPU total CPU time will finish earlier than the process with long CPU time. Okay, so that's good. Now let's discuss the time quantum even further for the round robin. Now, what the round robin going to look like if I increase the size of the time quantum? So we're going to do 2 things. First, we try to increase the size of the time quantum. Let's see what the round robin going to look like. Now, suppose that we increase the size of the time quantum to the extreme case. Let's say Q equals 4, which is the size of the total CPU time for process 1, and also the size of total CPU time for process 2. And it's larger than the total CPU time than process 3. So let's actually doing the same, draw the same timeline. So that's 10, and that's 0. So that's 4, and that's 8. Because the time quantum is 4, so let's say we only draw from 0 to 4. So once P1 is loaded, if P1 is at the head of the queue for the round robin, so P1 will be selected. So P1 takes the CPU time. You're going to run for 1 time quantum, which is 4, right? And then P2 start to run, and it takes 4 time quantum. And then P3 start to run, and in theory, P3 can run for 1 time quantum. So which means P3 can run from 8 all the way to 12, right? Because P3 can run 1 time quantum. Now, because P3 is smaller than 1 time quantum, so P3 actually terminates at 10. So, and then P1 has done its job, right? P2 has done its job. Now, what does this diagram look like? It just looks like the FIFO, right? Okay. So, when Q becomes larger and larger, the round robin looks more like a FIFO. Okay. So that's why we normally don't want to make the Q large. Okay. But what about if we try to make the Q smaller? Now, in general, making the Q smaller will still work. Okay. Now, what happens if the Q is extremely small? Okay. Now, before we discuss this, let's take a look at these example again when Q is 1. So when P1 complete the job, it will switch the scheduling algorithm, the round robin, gonna switch the process from P1 to P2, right? So then when you do the switching, there is a context switching time. Remember the context switching time? It's a time that the operating system used to, save the data for process 1 into the PCB of P1. Save the data into PCB 1. Because when P1 is loaded again, it requires to load the data from PCB 1 to the CPU again. Okay. And then when it's complete to save the information of P1 to the PCB 1, it will load the data from PCB 2 into the CPU. So P2 start to execute. Okay. Then we do the context switch again here when we switch from P2 to P3. So it will be save the data to P2, PCB2, and load the data from PCB3, right? And then once it's done, so the data will be saved to PCB3, and then the data will be loaded again here, right? So the context switching happens, okay, when the CPU switch from one process to the other. Now, in many cases, when we do the analysis, we tend to ignore the context switch time. Why? Because if the context switch time is extremely small, it's small relative to the time quantum. Now, for example, the time quantum takes 1 time unit, and the context switch only takes 0.01 time unit. So that's only 1% of the time quantum. So most of the time we can ignore that overhead. So the context switch is the time that the CPU does not do any meaningful job. It's just an overhead. It's just waste of the CPU cycle. Okay. So now let's take a look the other case. So we discussed the context switching time. Let's take a look at the case when Q is extremely small. Now you can make the Q small. That's fine. That's okay. And then you can switch. It's just like using the round robin. The CPU just switch back and forth among the processes more frequently, right? If the Q is small. Okay. So if the Q is half of, let's say if Q is 0.5, then the round robin gonna switch back and forth more frequently than when Q is 1. It's actually double the it's double the number of time quantum. So each quantum going to be half the original one. So it's half of 1. Now, that's okay if the context switch time is still smaller than the time quantum. But what about the Q is extremely small? Let's say I make the Q small enough so the Q takes the same amount of time as a context switching. So let's say I run P1 for 1 time quantum, but I take the same amount of time for the context switching, and then run the next process P1, P2, and take the same amount of time for the context switching, and then switch to P3, and then take the same amount of time for the context switching. Okay, remember the context switching is the overhead. So that's a big problem because now the CPU utilization is extremely low, because in this particular case, you run this, CPU execute for the process and then spend the same amount of time doing the context switching, which is basically technically doing nothing. So the CPU utilization is only 50%, right? That's pretty big. So half of the CPU time is wasted on the context switching. Now compare with only 1% of the time, wasted on context switching. Now it's 50%. So you cannot, make the Q extremely small. So that's something you need to pay attention to. So you cannot make a Q extremely large. You cannot make the Q extremely small. So round-robin scheduling treats all processes as equals. For an operating system supporting the round-robin scheduling algorithm, it creates a queue. Now, all the processes are going to be placed in the queue, and the scheduling algorithm is going to select the process at the head of the queue and allocate the process into the CPU. Now, once the process completes its job, then it will be placed at the tail of the queue, and then the operating system scheduling algorithm is going to select the next process at the head of the queue. Now, this is actually going to go on. So, if a process or operating system wants to support multi-level priorities, then a single queue for round robin is not enough. So the operating system needs to maintain processes in the queues at different priority levels. So that's called multi-level scheduling. So multi-level scheduling maintains a separate queue of processes at each priority level. Now, with each level, processes are scheduled using the round robin. Okay, so let's say here we can say it's a priority level. Now we have a priority level n, okay, and there is a queue, and then for priority n-1, the operating system is going to create another queue, n-2, it will create another queue, and so we go all the way to priority level 2 and then priority level 1. Okay, so then these queues are going to be used by the scheduling algorithm to allocate the CPU. Okay, so let's say a process, when a process is created, the operating system is going to first check what's the priority of the process and place the process in one of the queues. Okay, let's say I have 3 processes. Okay, at the priority level n-2. And the first process is called S, T, and V. And there's one process at the priority level 1. Let's say it's U. Now, the operating system scheduling algorithm, the multi-level scheduling algorithm, gonna check each of the queues and select the process in the queue, the highest priority level queue, and put the process S, which is at the head of this queue, into the CPU. So S is running now. Okay. Now, when the process S completes its job, and then it will be placed at the tail of this queue. Okay. And then the ML, multi-level scheduling algorithm, going to check all the process again and find out, okay, n-2 is still the highest priority level, which contains the processes. And then it will pick the next process at the head of the queue, which is T. So T will be placed into the CPU, right? S has removed from the CPU and placed at the tail. And then when T finishes, then T will be placed at the tail again. So this one going to be removed. Okay. So now, as far as n-2 is the queue, that the highest priority queue, and then the operating system scheduling algorithm, the ML scheduling algorithm, are going to continue to run that way until the operating system create another process, and then that process has a higher priority. Let's say W, and then W is actually placed at the priority level N, which has a higher priority, and then whatever actually is running in the CPU will be removed and placed at the tail, okay, of that queue. And then the operating system scheduling algorithm, the ML scheduling algorithm, is going to load W into the CPU. Okay, so that's the multi-level scheduling algorithm. So when the maximal time allowable for this level expires, the running process moves to the tail of the same queue. So that's what we actually seen here. And if a new process with a higher priority, higher than the current running process, preempts the running process. So W going to preempt any process at this level because W is at the priority level M. So it will preempt any process at the level n-2. So actually it will preempt any process running below priority level n. Okay, so that's the ML scheduling algorithm. So we basically summarize the multi-level scheduling algorithm here. So we have different levels, priority levels. Okay, so every time the scheduling algorithm is going to schedule the process at the highest priority queue. Okay. Now, the multi-level scheduling algorithm can solve some of the problem that a single round robin cannot resolve because each level uses the round robin, right? However, there's one problem that the ML scheduling algorithm cannot resolve. Now that's the starvation. Now let's take a look at this process U, which is at the level 1. That's the lowest priority level. Now process U doesn't have a chance at this moment because there are many processes above this level 1. So then process U will get a chance to run only after all the processes above this level 1 are completed, so then it will get a chance. Now, what about at any time there's always a process running above level 1? So that means this process you never get a chance to run the CPU. Now that's the starvation, right? And the multi-level scheduling algorithm cannot solve the starvation problem. So we're going to come up with another scheduling algorithm. Okay, let's see. Okay, let's actually introduce a new scheduling algorithm. Now it's called a multi-level feedback scheduling algorithm, MLF. So multi-level feedback scheduling algorithm is similar to multi-level scheduling algorithm, but it addresses the problems of starvation and fairness by using a different time quantum at each priority level. Okay, it will change the priority of each process dynamically. So using the multi-level feedback algorithm, so then you're going to still continue to create a different priority level, just like a multi-level scheduling algorithm. So I have a priority n minus 1, priority n minus 2, and I have priority 1, something like this. Now, for each priority level, just like a multi-level algorithm, we use round robin. Okay. Now, instead of actually assign the priority for each process, using multi-level feedback scheduling algorithm, now we're going to use the round robin. At the top level, we're going to use a round robin with, let's say, time quantum Q. And then in the next level, a lower priority level, n minus 1, we're going to use 2 times Q as the time quantum. And then the next one going to double again, 4 time quantum. So the next one going to be 8, 16. So at the level 1, I don't know what's the, let's see, level 1 going to be, it's going to be time quantum, which is very big time quantum. Let's say assume that it's 2 to the n. Let's see, what's the value? N minus 1, I believe. Okay. Yes, I think so. So then this is the first Q, which is support round robin with time quantum Q. And this is the second Q, is also use round robin, but support the time quantum 2 times Q. And the third one times 4 times Q. Okay, and here's the CPU. Okay, the last one use 2 to the n minus 1 times Q. Okay, so each time when a new process is created, it was placed in the highest level Q. Okay, so in the priority level n. So if the new process is created. Now, because this process is actually at the highest level Q, and then if there's some other processes in the highest level Q, another process in the highest level Q, and then it would use the round robin, the process, at the head of the queue will be selected. So let's say ST, that's the time quantum V. So that's okay. So S will be selected, right? Okay. Now, once S actually complete the job and run for like a one time quantum, which is Q. So then S will be placed in the next level. S will be placed in the next level. Okay. So the priority of this process S will be reduced from priority n to priority n minus 1. And then if there's another process in the highest level, priority level n, so then the next one at the head of the queue will be selected. So example, now Q is actually moved and placed in here, or S is removed and placed here. And then T will be allocate the CPU and run for one time quantum, because that level in the Q in the level M, it will run as a round robin using time quantum Q. So once T complete job, T will be placed over here. Okay. So every time when a process is created, it will be placed at the highest level, priority level queue. So that's priority level n. Okay. So then once it's run, the process is running at the level n one times using round robin. So if they still have remaining, then the remaining of these process going to be placed in the second level priority queue. That's n minus 1. And then if there's no actual process at the top level, level n, then the process at the second level, n minus 1, will be picked based on the round robin scheduling algorithm. Okay. Now, if that process in the second level, after run for one time quantum, which is 2Q, and it's still not finished yet, so then the process is going to be placed in the third level queue, n minus 2. So it will actually, the process of the priority of the process is going to be going down. Okay, until in one of the priority level, then the process actually completes its job. Okay. Now what's different between the ML and MLF? Okay. Now under the multi-level feedback, MLF, a newly arriving process enters the highest priority queue, N, and it is allowed to run for Q time units. Okay. When Q is exceeded, the process is moved to the next lower priority level, N minus 1, and then is allowed to run for 2Q time units. Okay, so the quantum size doubles every time when it's completed at this level and move down to the lower level, but the quantum size is going to be bigger. Okay, actually it doubles. So now let's see what's different between multi-level and multi-level feedback. So multi-level feedback automatically favors short running process, while process with long running time gradually migrate to low priority levels. So if the total CPU time is very small, then the process is going to be completing very quickly. And if the total actual CPU time is very long, so it will be complete in the high level and move down to the next level, move down to the next level. So, it will actually, it will finish. Actually, it'll take a long time to finish. So that's the multi-level feedback queue. So it basically favors the short, process. For the long process, it will take a long time to complete. So that's a multi-level feedback scheduling algorithm. Now let's talk about the performance of interactive scheduling algorithm. Now, for interactive scheduling algorithm, normally we're going to measure the response time of a process. So the response time of a process is the elapsed time from the submission of a request until the response begin to arrive. Okay, so now if there's only one process running, the response time depends on the type of request. So for example, if you press the key and type certain of the characters, and then seeing the characters appear on the screen should be imperceptible by the human eyes. So you're probably going to see it appears immediately. Now the request to spell check a document or render a video clip could take a few seconds. So once you actually click to do the spell check and until it's a complete job, you may see some kind of delay. Okay. Now when multiple process time shares the CPU, then this is going to increase the response time for each individual processes. Now let's take a look at the following. So now let's take a look at the time sharing performance with various different scenarios. Now in case 1, if there's one process running on a computer system, now the response time is the interval between making request and the received response. So making request, receive response. That's only one time unit. Now in this case, CPU is actually dedicated to the process. So 100% of the time, CPU is working with the process P. Okay, so the delay, so the response time is one time unit. Now, in the second scenario, I have two processes, P1 and P2. Now, P1 and P2 time shares the CPU. So P1 only gets half of the CPU time, right? Another half is actually given to P2. So now, what's the response time? Now, the response time over here is 1, because even in the first case, it's 1. But now, so the first process experiences two additional units of response delay. Now, during this time, process 1 has to wait. Okay, so then that's 2 additional time for P1. So that means the P1 experiences a response time of 1, but it will experience 2 additional time. So the total response time is going to be 3. Now, let's take a look at another scenario. In that case, you have a time sharing between P1 and the P2. Now, also, the quantum is 2 units, right? Again, the time quantum is 2 units. But the context switch overhead is 1 time unit. So the red color represents the context switching, context switching, context switching, and the context switching. Okay. So that means pretty much 1/3 of the CPU time is wasted on context switching. So the useful CPU time is reduced to 2/3, which is 60%. Okay. Now, this useful CPU time has to be divided between P1 and P2. So P2 only get 66 divided by 2. That's only 33% of the CPU time. Now, because of this, the response time increases to 5. Why? Now, original response time is 1, but then you add 2 additional delay because of the time sharing. That's for the process 2. And then you add 2 additional context switching time. So that's 1, that's 2, add 1 again, plus the original 1. So it's a 1 plus 2 plus 1 plus 1, so that's total of 5. Okay, so that's a total of 5. Okay, now let's take a look at another scenario. So we still have P1 and P2. Now let's increase the quantum to 3 times. So let's say that's the quantum, time quantum. So the time quantum used to be 2, but now let's increase the time quantum to 3. And here's the time quantum 3, time quantum 3, and then the context switching time is 1. So that means the useful CPU time is 3/4, right? Only 1/4 of the times are wasted on the context switching. The 3/4 of the time is useful time. So that's 75%. Now, you're going to divide this 75% between P1 and the P2. So P2 and the P1 only gets half of this 72. So it's just 37.5%. Now, because of the increase of the time quantum, now you find out there's additional delay. So this is the delay. Okay, so that's response time. Now that one, the context switching is additional delay, and then P2 going to take one time quantum, which is 3 now, and then additional context switching. So it's a 1 plus 1 plus 3 plus 1. So total response time from the time it makes request to respond, that's total is 6. Okay. It's getting worse and worse and worse because first time you have one process, second time you have 2 processes, and then the third time you have to count the context switching time, and the fourth time you increase the context time quantum. Now, let's say another case scenario. Now we increase the number of processes from 2 to 3, and still use the time quantum 3. Okay. So then, what's the response time now? So that's the original response time 1, and then that context switching is cause 1 delay, 1 unit of delay, and then that's a delay of 3, and another delay of 1, delay of 3, another delay of 1. So it's 1 plus 1 plus 3 plus 1 plus 3 plus 1. That's total of 10. So you make a request here, and you respond here. It's getting worse because more and more processes start to share the CPU. Okay, so basically the useful CPU time is still 75%, but this time this 75% of useful CPU time are shared among 3 processes. So it's going to be divided by 3. So that's only 25% of the time. So in this case, using the time sharing, the more processes you include, the less CPU time each process is going to get. So the longer response time you will experience. Thank you.